One of the things I like about particle physics is its ability to describe the behavior of matter under every experimental condition we've ever investigated. We call our very successful theory the standard model of particle physics. I made another video that describes this incredible theory. While the standard model covers most of the known fundamental forces, specifically electromagnetism, the strong and weak nuclear forces, and the Higgs field, this model says absolutely nothing about the force that literally binds the universe together, the force of gravity. The reason for this is simple. Gravity is incredibly, ridiculously weaker than the other known forces. On the size of, say, about the size of the atomic nucleus, the other forces all have kind of sort of the same strength, with the weak force being about 100,000 times weaker than the strong force. Now that last statement probably sounds kind of silly because 100,000 sounds like a big difference, like comparing something 4 inches tall to Mount Everest. But gravity is unfathomably weaker still. It is about, wait for it, 100,000 trillion times weaker than the strong force. That's like comparing the tiny proton to the size of the visible universe. It's a huge difference. Since gravity is so weak in the quantum world, there is no chance that we'll ever see any effect due to gravity in a particle physics experiment. In fact, if all we had to go on was the data from particle physics experiments, we wouldn't even know gravity existed. The reason that we know of gravity is because it has an infinite range and up to size scales of the Milky Way or even clusters of galaxies that we can see it works basically like Isaac Newton predicted 350 years ago. It takes the mass of asteroids or planets or stars to see gravity at all. But I don't want to talk about the gravity of the big, which is the domain of astronomy or cosmology, but rather I want to talk about the nature of gravity in the realm of the very small. But I just told you that at sizes comparable to that of a proton, gravity is very weak. So what the heck am I talking about? Well, gravity, even if weak, must apply in the microworld. Now, that's not a very profound thought, but it's true. And since our best theory of gravity is Einstein's theory of general relativity, the most obvious thing to do is just apply that theory to the subatomic realm. As an illustrative example, let's imagine an electron orbiting a nucleus. If you do that, you find that Einstein's theory predicts that the electron would lose energy by the emission of gravity waves and then spiral down into the proton. A similar prediction using classical electromagnetism led to the invention of familiar, or at least well-known, quantum mechanics. This same chain of reasoning suggests that gravity must also have some kind of quantum nature. Another reason to suspect that gravity must have a quantum nature is because A, we definitely have a quantum theory for the other forces, and B, general relativity is a classical theory. It is impossible to seamlessly wed a quantum and classical theory, and this is taken as additional evidence that there should exist a theory of quantum gravity. Otherwise, we'll not be able to write a theory that accurately describes everything in the world of the very small. So, if we accept the idea of quantum gravity, what do we know? Well, there are some basic conclusions we can make that are true for all such theories. One such conclusion is that there should be a particle called a graviton. In just the same way that a quantum theory of electromagnetism predicts that a photon exists, quantum gravity predicts that a graviton should exist. Now, we've never seen a graviton, which means that you shouldn't believe in it. But if it exists, in order to agree with both Newton's and Einstein's theory of gravity, the particle must have certain properties. To have gravity's infinite range, the graviton must be massless. To be only an attractive force, the graviton must have a quantum mechanical spin of 2, which is different from the electron's spin of 1/2 and the photon's spin of 1. The graviton must also be electrically neutral. So this all seems pretty simple. The theory predicts a particle with very specific properties. So it would seem that the next step would be to go out and find it. I mean, my colleagues and I do that sort of thing all the time, right? Of course, the problem is that gravity is so weak. And because it's weak, it's essentially impossible to make a graviton in a particle physics experiment. To all intents and purposes, there is no chance that we'll ever find a graviton, even using the accelerators we might imagine building with the technology of 100 years from now. There is one small possibility we might see a graviton someday soon, but that's only if the universe is much different than it appears. If the universe has additional tiny dimensions beyond the familiar 3, it's possible that we might find gravitons, and even possibly find massive gravitons as well. But this possibility is dependent on these small extra dimensions existing. Frankly, while it's possible, it's a long shot. If you're interested, take a look at my video on the idea. So, getting back to the more basic idea of quantum gravity, has there been any theoretical progress on the subject? Well, yes and no. There have been a couple of quantum gravity theories proposed that are kind of successful. And by successful, I mean that they're still possible. One is superstring theory, which says that the very smallest building blocks of matter are actually very tiny strings. This theory has been very popular for many years, although some have criticized it for not making testable predictions. If you're interested in the idea, check out my video on the topic. Another idea that's been floating around for a while is called loop quantum gravity. The mathematics of this theory is pretty complex and goes by the confusing name of spin networks. But the basic idea is that there is a smallest quantum of space and time. Now this is a pretty bizarre idea. It means that unlike ordinary sizes in which you can cut an object a meter long into two objects half a meter long, when you get to a certain size, you literally no longer can make smaller objects. The physical dimensions of this smallest space and time are too small to test in particle physics experiments, although they might have some testable consequences in observations of very distant astronomical objects. The jury is still out on these studies, but so far there is no evidence that confirms these ideas. So, there is no confirmation of quantum gravity, but if the idea is true, it has some real consequences that will change how you think about such cool things, such as the center of black holes and the universe right before the Big Bang. If you have even a casual knowledge of physics, you've no doubt heard that scientists think that before the Big Bang, all of the matter of the universe existed in a single mathematical point with zero size. Similarly, the center of a black hole is said to hold all of its mass of the parent star compressed to zero size. These tiny concentrations of enormous mass are called singularities. And singularities are unphysical. They don't exist. If a theory predicts them, then that's a sign that the theory has been pushed hard beyond its limits. Now, I do not want you to think that this means that black holes don't exist or that the Big Bang never happened. Nor do I want you to think that huge concentrations of matter in tiny, tiny volumes aren't real. All of these things really exist. So don't send me some anti-relativity email. But what I am telling you is that as matter gets compressed into smaller and smaller volumes, that gravity becomes more important and the theory of quantum gravity starts to dominate. Quantum gravity is what protects against a singularity. And what this really means is that we will never understand the details of the beginning of the universe or the center of a black hole until someone works out a theory that blends gravity and quantum mechanics. So I hope that this conversation gives you a sense of the complexities involved in a quantum theory of gravity. Realistically, solving this problem will take a long time, but it's a fascinating topic and one that we'll need to solve before we finally have a theory of everything.